Yes, I want to talk about BFDLAC, a fast lossless audio compression library, an update. So there was a talk last year. It's mostly based on that, but there have been some changes that I want to appraise everybody of. So we'll cover quickly what BFDLAC is in the first place, how does it work, the fact that we've now ported it over to ARM and Neon, whatever this mysterious thing is, and the fact that there's licensing available, and my ongoing investigations. So first of all, BFDLAC is an audio data compression codec. So it's not a dynamic range compressor, it's an actual data compression codec, and it is lossless, which means it has perfect reconstruction of the signal. It was originally designed to help us around a problem in BFD, which was an extremely large multi-channel, multi-velocity drum sampler that we built at F-Expansion. As our data set got towards 160 gigabytes, it was becoming increasingly impractical to actually stream that data quickly enough off a standard disk drive. A disk drive at the time could probably reliably stream maybe 100 megabytes if you were lucky, and our requirements from the sheer number of channels that we were streaming was well above that. So we needed to go to a disk streaming compressed format. FLAC was not fast enough. We were using FLAC already to install our data, but we needed something much, much faster than that. We needed also to support more than the 8 channels that is native to FLAC. Some of our BFD packs actually go up to 31 channels now, and the BFDLAC format has room for 256, curiously byte-aligned. We also wanted to be able to support random access during disk streaming, which is again quite hard with some of the formats like FLAC, which rely on encoding or decoding each frame to work out where they're up to. And because it's developed for a sample library, we're going to absolutely prioritize decode speed at the expense of any kind of encode speed optimization. So if it takes us half a day to find the absolute best encoding algorithm, we will do that because we know it's going to be used millions and millions of times more to decode. So that's where we want to concentrate all our effort. Just want to quickly look at what our standard source data was, a drum sample. At the beginning of a drum hit, stick hits some sort of object, there's a loud noise, broadband noise burst, which is typically quite hard to compress because it is random energy going in all kinds of directions and all kinds of frequencies, but it's only short-lived. The vast majority of a sound in wave format is a long decaying tail of the drum sound, which can go for tens of seconds in BFD's case. So this is a major feature that we need to focus our efforts on. The harmonic structure can be simple in the case of a tom drum, mostly a sinusoid, or complex in the case of a cymbal, so our algorithm needs to be able to deal with both. And interestingly, considering that we were dealing with 24-bit audio, the noise floor is often about 90 dB, or in other words, about 8 to 9 bits of the data that we're shipping to all our customers all over the world is garbage. And that is because customers lust for vintage gear that has that warm analog all the way through the bottom of it. So to summarize, all the stuff in red is probably bits we don't need to encode. So what we want to do is basically choose a lot of very, very small blocks where we can say, okay, the noise is going to be roughly constant for each of these small blocks, and we're going to come up with incredibly simple algorithms that encode the macro shape of the WAV that isn't the noise within that block. And using this very, very simple approach, we can throw all our effort into SIMD optimizing everything. Another little diversion, I want to look at our data consumption patterns because we want to emphasize the decode speed. So a multi-channel audio file can be encoded as either a interleaved, typically interleaved or non-interleaved format. So when you have a non-interleaved audio file, it means all your left channel samples are next to each other and all your right channel samples are next to each other, which is great if you're doing within channel processing. Terrible for streaming though, because if you have a very large WAV file, it means the read pointers for each channel have a great separation in data space. An interleaved format, you have the left and right channels next to each other, so you have good cross-channel locality, but if you're trying to do within-channel processing, you need to step over each samples. And when you're only dealing with mono, stereo, that's fine, but if you're dealing with a 31-channel drum sound, then it becomes quite problematic because you actually start blowing the cache lines every time you need to get to the next sample in your sample frame. So we want to come up with a hybrid format where at small frame sizes, all the samples for a channel were next to each other, and then as you move out, you actually have an interleaved format at a slightly larger scale so that you can stream the data efficiently, but when you're actually synthesizing extremely locally, all the samples are next to each other. I seem to have that twice. Let's get over that. So the BFDLAC file structure, it's a RIF-like file format. It's all chunkified. We have a format chunk that specifies things like the channels, the length of the file, and the target bit depth. BFDLAC will quite happily support 32-bit decodes, but if you've only got 16-bit data or 12-bit data, we can decode to that, which can be useful if you're coming up with, say, a demo version, which only has reduced bit depth or something like that. A very important chunk is the index chunk, which has like chapter headings all the way through the file, so that if we need to get to a 1, 2, 4, or 8K sample boundary, then we can use that as a fast lookup to go exactly to where we need to go. And then the data chunk, obviously where the bulk of the data for the file lives, we have the audio broken up into frames, which contain, which is a multi-channel structure of blocks. A block is a single channel structure, and that's the data temporally localized single channel all next to each other thing. So within a frame, we have a frame header byte, which says how many channels are in the frame, and that's constant throughout the file, and we can use that for debugging. So if we hit a frame number or frame channel count that we don't expect, it's like, oh dear, something's gone wrong. The most important byte in the block is the 1 byte, the header byte, which actually encodes two very important things: which one of the 16 sub-algorithms we use in BFDLAC to encode just that one block of data coming up, and the all-important how many error bits are we also going to encode. So that one block header byte fully determines the length of the block that follows, which means that if we're not using a channel, we can skip over it very, very quickly without having to decode it to find out how long it is, which is a feature not found often. So the encoding strategy is a very commonly used signal plus residual noise type of thing. As I said, we've got 16 block encoding sub-algorithm spaces, of which about 10 are used. And when we're encoding a sound, we just go through and evaluate them all, and whichever one turns out that it can actually support the current signal going through it and is actually the smallest, because we have a deterministic block size, that's the one that gets selected. So as we find more and more algorithms that work with this kind of data, we'll just go through and evaluate them all. The noise, as I said before, is encoded with a fixed bit depth per block, and that means that we can go to town on the SIMD vector instructions. And I'm going to coin a new term that the approach used in BFDLAC is a bottom-down approach, where we find some very, very simple maths, the absolute bottom of the barrel, and then we head down towards the actual silicon as fast as possible. And it's all about speed and simplicity. It might be called a vector-optimized lossless audio compression. Might be a better name, which does sound a little bit like it might be some sort of 1970s Japanese anime character. I think that's actually Zoltar, one of my favorites. So let's have a look at some of the BFDLAC block sub-algorithms. Like I said, they're all quite simple. There is no encoding. There is zero or constant encoding, the actual zero value, median plus some sort of error, a gradient, first, second order linear prediction, and some variations on that, quadratic regression. None. So we often use for the transient, you just copy that wave data straight in, and because that tends to happen at the beginning of the sound, and you're probably going to have to pre-cache your sound before playing it in your sample library playback engine, that's actually not such a bad thing. 0, this is a really interesting case. 1/3 of BFD data is zeros. So efficiently encoding 0 is actually a much bigger deal than you'd expect. In a multi-channel drum library, sample library, you have near mics, far mics, mics a go-go, and the near mics often tail out much faster than the ambient room mics, and so they effectively go to 0 very quickly. So yeah, our 0 packs what would normally be 196 bytes of 24-bit data into 1 byte, which is great. And there's quite a bit of data. Well, from a BFD point of view, 0.3% of data is still some hundreds of megabytes, so actually being able to encode constant is useful as well. Gradient, very, very simple, first order linear regression. That's still almost 5% of BFD data. We have BIFs. We're getting into, hang on, that's linear regression. That's the beginning of LBC now. The 33% of BFD data encodes with diff, very, very important. So lots of time spent optimizing that stuff. One of the problems with diff is that because each sample depends on the previous sample, that's one of the harder ones to actually SIMD optimize. We can obviously SIMD optimize all the actual error signal, but not the primary maths, which is a shame. Working on that one, but we'll see what we can do with middle out, my first Silicon Valley reference of the day. So what does this actually get us? Let's see where the BFDLAC results go. So in the BFD3 library case, we had 160 gigabytes of sound of WAV. FLAC can compress that down to 34, and BFDLAC manages to bring it down to 40 gigabytes. And so you can see the compression ratios that FLAC's 21.3% of original size, BFDLAC is 24.8, not that far behind. But the really interesting thing is the number of real-time channels that a single core of my test machine at 3.5 gigahertz Haswell i7 with AVX2 enabled, 1 core, the number of decode channels it can support. So at RT chans, we can decode 750 channels of FLAC or 18,000 channels of BFDLAC. And the final column is the number of clock cycles per sample generated. FLAC is about 106, and the BFDLAC is 4.4. So yay, SIMD. SIMD is great. If only we had a way to measure this kind of metric which combined both the speed and the compression, such as the Weissman score. Thank you, Silicon Valley reference number 2. So here we have R is the compression ratio, the original size over compressed. T is the clocks per sample decoded. R dash and T dash for our reference algorithm, which is FLAC. And what do we get for BFD? We get this magic number 2.67, which sounds fantastic. If only Weissman had any meaning in the real world, but there we go. So can we use BFDLAC for other non-drum sounds? So after my talk last year at ADC, I had some people coming up saying, well, I had something that's kind of like a drum sound. It's a percussive sound. It's a piano. It's like, let's try running that through. And yeah, piano works pretty good. So do violins, which was even more surprising. Percussive I was expecting to do, but yeah, other single channel or single voice sounds are actually not too bad either. So here is an anonymized another data point. We have the stats for this other mysterious library. So you can see that FLAC is still coming through smaller by 20%, but BFDLAC is 13.5 times faster to decode, which is great. So why was there the big difference between BFD data and this? BFD data has a lot of zeros in it, and the reason why it gets the 18, well, the 20, was it 23 times faster? Yeah, 24 times faster for BFD, for drum data is that there are some parts of drum data which are much easier to decode than a pitched sample. Do we have a Weissman score for that? Yes, we do. 1.918. Make of that what you will. So we have put a juice interface on top of BFDLAC. So you can now use BFDLAC for decoding with a standard audio format and audio format reader. So in theory, you can drop it in. We have BFDLAC as an OS X, Windows, iOS library, beginnings of Neon optimization. It supports multi-threaded decoding. You can have multiple reads of the same file happening at once, which is important because a lot of people with sample libraries like to deliver their sample data as one big monolithic payload. At the moment, because of the RIF file structure from original BFD, we're limited to 32-bit, i.e. 4 GB file sizes, so we've got to start thinking about making the jump to 64-bit. At the moment, there's no audio format writer, and that's because of the index file and also some curiosities with Juice, which are very steered towards streaming, whereas BFDLAC kind of likes to know when the end of the file will be at some point so it can get around to building the index, but that shouldn't be insurmountable. For anybody who is looking at porting their wonderful SIMD optimized or their SSE AVX optimized code over to Neon and hasn't faced it yet, you're in for a treat. When you go to look at the the ARM documentation for Neon, it is a delight if you've been suffering SSE and AVX on Intel's website for many years. There's like an orthogonal instruction set, good heavens, and the documentation actually explains what all the parameters do. This is mind-blowing. There are some things which are problematic in that ARM only goes up to 128-bit operations at the moment, and some of the operations are needed to use in BFDLAC are still only represented as pairs of 64 bits. But yeah, Neon's great. So one of the new features in Juice recently in the DSP module was a SIMD register class, where we're trying to abstract the difference between SSE, AVX, and Neon. And so with a few more little additions, I'm going to try and port all of BFDLAC over to use that, but there's a few little things needed first. Oh, here's another example of a BFDLAC sample library running on an iPad and the sort of numbers that we see from that. FLAC in this example was getting about 300 voices, channels per second. BFDLAC enabled a 6 times boost to that up to 1800, which is great. So current explorations, looking at more complicated stereo encoding so that we can take advantage of cross-channel correlation. Quite a lot of BFD's channels are mid-side encoded if they're room mics and things. So I did an experiment where I just turned off the mid-side encoding and encoded it normal way versus the way it actually is in BFD, and that made a 1% difference, which, you remember, 160 gigabytes, that's 1.6 gigabytes worth of improvement, so that was great. More exploration of what I'm calling a higher order sparse linear predictive encoding. In other words, just finding a couple of higher order. Yeah, the problem with any new algorithm in BFDLAC is you really just want a couple of bytes to define all the coefficients. So it's really about carefully trying to put in only what you need. But I mean, that's compression in general, I guess. Greater monolithic file support, as already said. Low frequency noise bit encoding, that's where if there is a block of 8 samples, for example, that need an extra bit to encode the residual, then they get them, but the other parts of the residual don't. So sort of like a multi-resolution noise encoding approach. And the middle out, the other reference, LPC encoding. So I've got a graph, not a graph, I've got a table to show what the hell I was going on about last time, which is your typical differential encoding. You start with the value, you add your error and go on to the next one. But if we go both ways at the same time and start in the middle and go outwards, then in theory you've got 2 independent math streams going on, which will keep the various math units of your CPU going. Yeah. That's it. So is BFDLAC a good format for you to deliver your sample data? Talk to me and we'll talk science. And if you're BFDLAC bi-curious and want to know more about the licensing terms, talk to Jean-Baptiste and we can do business. Thank you for your attention. I will take questions.
So, if anyone has a question, I can give him the mic. Okay.
Thank you very much for that, SkoT. I was just trying to write a lossless audio compressor last week.
Oh, good.
So your speech has been fantastic. What did you think about rice encoding of residuals? And part two, did you benchmark different block sizes, and what was your experience there?
So the reason why I didn't do rice encoding is because it's a variable length encoding scheme for the noise that doesn't allow you to use lots and lots of SIMD all over the place. So that was a deliberate decision to say we're going to lose a little bit of space, but we're going to absolutely go to town on the 64 blocks of the 64 sample blocks of noise. And then did I test different block sizes? Yes, the original version of BFDLAC actually had variable block sizes, 128, 64, 32, and it turned out that 64 was coming through all the time, and I actually had a better use for that bit that was encoding the block size, and I decided, right, instead of having the original noise encodings were only 16, 12, 8, and 4-bit depths, and I thought if I take the two block size bits and put them over on to have a full 16-bit range, it brought down by another 3.2%, which is extremely exciting.
Thank you very much.
Yeah, those partial percents get really exciting. They come down and say, oh, dear wife of mine, I've just knocked off another 0.2%. It's very nice, dear. Go off to the pub now. I was like, great.
Any other question?
One thing I took out of the talk this time, because I looked at last year's talk and realized that trying to show a SIMD optimized noise decoder requires more lines than comfortably fits on a screen at a reasonable font size. That one of the greatest instructions that appeared in AVX2, AVX2 is the variable bit shifty thing, where if you've got something like a noise signal that is encoded at 7 bits, and you've got 128 bits worth of little 7-bit numbers, and you're thinking, how the hell am I going to stick that into 32-bit int chunks? Being able to copy little bits of your 128-bit. Hang on, I'm going to actually get up my slide from last year because this is ridiculous. You do actually need to see it. I also got rid of slides like this, which was great fun. Try to make it a little bit more professional. Where did it go? Ah, here we go. Yeah, this guy. Whew. Is this going to help in the slightest? Where is my favorite new instruction? Oh, I'm not allowed to. I've got to stay here. Sorry, people on the internet. I've lost it. AVX2. Yeah, somewhere around about here. The variable logic bit shifts. Okay. It is important to know that there are two types of bit shifts in the world. There are arithmetic and there are logical. And if you have a signed 7-bit int that you need to get back into normal variable space, sticking those 7 bits in an unsigned int, taking it up to the top, and then leaving that signed bit and bringing it back down again. So in normal C, you'd have to do it as an unsigned variable, do the shift, swap it over to a signed, and do the shift back in C++. But if you're down in assembler, then there are actually two explicit bit shifts, the arithmetic and logical. It makes it so much easier. Yeah, and ARM Neon has really, really good coverage of that kind of space as well. That was a random rant. Okay, more questions? Steer my brain, please. Everyone's now terrified.
Okay, so thank you very much, SkoT, again.
Thank you.